Good afternoon. I'm Joan Cotter. I'm recording this in Minnesota because my doctor recommended that I not travel because of the current health crisis. First, I'd like to give you a little bit of my background. My first degree is in electrical engineering from the University of Wisconsin-Madison. Then I also received a PhD in mathematics education from the University of Minnesota. My diploma was given to me by Mario Montessori, and I did start a Montessori school in my hometown. I also taught a year as a special education teacher in a Montessori classroom. Math has greatly changed since 1907. Math itself has greatly increased. In fact, it's been said that mathematics is doubling at the rate every 7 years. Many of today's mathematics algorithms did not exist in 1907. One of the major ones is statistics. And the applications for math has really exploded. Math is used in so many different ways. And tools for calculations. We're all familiar with calculators and computers. They has greatly changed the way math is used and also has furthered the math field itself. We also have refined measuring devices. For example, telescopes, and even on the smaller level, spectrometers. We also have done research into better teaching methods. We can now see what parts of the brain light up when we're learning certain things. This has all greatly changed the way we teach math. A person whose lifetime showed this huge change is Katherine Johnson. You probably have heard of her. She's from the Hidden Figures. But notice what's on her desk. That's a mechanical calculator. I actually used one of those in one of my first jobs. This is before the electronic calculators. She worked at Langley Research Facilities in Hampton, Virginia in 1953. That's when women did the calculations and the men were the engineers. When computers were started to be used to calculate trajectories, John Glenn actually asked her to do the calculations by hand. After all, his life depended upon it. And he wasn't the only astronaut whose calculations she calculated. She also did Neil Armstrong's. Shetterly recorded her story in the book Hidden Figures. She's received several honors. BBC placed her on the list of the 100 most influential women. Barbie doll was made by Mattel in her likeness, and NASA named a new building after her. And keep in mind, she was a Black woman. She was a pioneering Black woman. Now, my rationale for doing this comes right from Montessori's book written in 1912. She says, "This book of methods compiled by one person alone must be followed by many others. It is my hope that starting from the individual study of the child educated with our method, other educators will set forth the results of their experiments. These are the pedagogical books which await us in the future." I want you to understand how many, what counting is like for a child. This is 1, this is 2, 3. When we say 3, we obviously mean all 3, and this is 4. But the very young child does not see that. When you say 1, they see 1, of course. 2, they've lost the 1. They think that you're naming that number 2, and that's 3, and that's 4. In fact, if you were to ask a child to bring you 4 after they've counted them, they'll just bring you the last one. Now I want to do a little exercise, traditional counting. Because we're so familiar with the numbers, we're going to use the letters of the alphabet. So A is 1, B is 2, C is 3, D is 4, and so on. Now let's try adding F plus E. Well, first we have to count out F counters. A, B, C, D, E, F. Now to add E, we have to count out E counters. A, B, C, D, E. How much is this all together? Now the answer must be a letter. Well, it's going to be K. A, B, C, D, E, F, G, H, I, J, K. You understand adding? All right, now find the sum without counters. What's E plus D? Now try G plus E without fingers. Getting more difficult. Memorize the facts. Okay, let's try subtracting. What's H minus C? You can do this by counting backwards in your fingers. Try it. Try skip counting by B's to T. And what's D times E? Kind of overwhelming. Well, some schools, and it's even crept into Montessori schools, have been using calendar math to help children memorize the counting sequence. But there's a few problems. Let's have a look. Here's the month of March. Now, if you count on the month, 1, 2, 3, 4, there's a little problem there. Because does 4 include 1, 2, and 3? No, this is not cardinal counting. Day 4 does not include the first 3 days. Actually, it's ordinal counting. We should be counting this as first, second, third, fourth. And then sometimes people use the calendar for patterns. Really, patterns rarely proceed in rows, and they certainly do not stop at 31. And also 7 is not exactly an exciting number. The day of the month can be shown a variety of ways. You can circle them or use a different color, all kinds of ways. Children are often expected to know what number comes next without starting from 1. If you think that's easy, think about the nursery rhyme Jack and Jill. What word comes after hill without starting from the beginning? Could you do it? Well, the answer is 2. Naturally, it's a number. But didn't you know Jack and Jill well enough to do this? Now let's take a look at counting in general. It is not natural. It takes years of practice. Even in children who grow up in languages that do not have counting words, they don't automatically make up new words. Provides poor concept of quantity, ignores place value. Where's the place value when you say 11, 12, 13? Very error prone. I don't need any examples for that. Tedious and time consuming. Does not provide an efficient way to master the facts. And it is not predictive of future achievement in math. Psychologists are always looking for these little things that make a difference in a child's overall math. And there are some difficulties learning to count. Children with dyslexia or dyscalculia have a terrible time learning to count to 100. Children with specific language impairment, that's those children who don't talk till they're 4 years old or later. Children with memory challenges. And today we are having more children with these kinds of problems because of more premature babies are surviving and children are surviving cancer treatments. We now know that a child who's had 3 surgeries by age 4 will never recover cognitively. And they'll always be having these difficulties. Children with poor motor control, those with cerebral palsy and other diseases. And children from low SES backgrounds. They don't have the adult in their life to drill the numbers up to 100. But is counting the core of math? Actually, counting is used primarily in arithmetic, and arithmetic is only one of 200 branches of mathematics. Believe it or not, abacuses were designed to make counting unnecessary. Counting to determine quantity is inefficient. It's very slow for multiplying. And it doesn't work for money or for fractions because children then tend to add the denominators as well as the numerators, or with money, they think each coin is worth 1. Counting is very pervasive in Montessori materials. Notice it's in number rods, spindle boxes, golden bead materials, snake game, dot game, stamp game, multiplication board, and the bead frame. Well, I wondered for a long time, why did Montessori have so much material for counting? And I think I might know. Remember, she taught slum children in Rome, and children who had any problems, mental or physical, were sent off to asylums. And they had a test to see whether a child was physically fit or mentally fit. They didn't have IQ tests in those days. But one of the questions on the test asked to see how far they could count. So Montessori, I believe, wanted to make sure that children could count so they would not end up in those asylums. An alternative to counting was developed by Karen Wynn. Actually, she published her first research in 1993. She showed 5-month-old babies, she had them sitting comfortably, and then she showed them 2 teddy bears, covered them up with a screen, and then showed the baby a 3rd teddy bear, put it behind the screen. Now the baby never sees all 3 of them together. The screen goes down. If the baby sees 3, the baby won't look very long, because the baby, like us, will look at something new or novel longer than something that's familiar. Well, they expected 3, so ho-hum, they didn't look very long. The researchers time how long the babies will look. But the sneaky researchers can change the number behind the screen. So let's say the baby only sees 1. The baby will look significantly longer, as if to say, I know there were 3. What did they do with the other 2? And she's done some really amazing some studies with this in Yale University. You can actually go there and have your baby tested if you live nearby. So in essence, infants can determine quantities long before they can count. They can add and subtract 1 to 3 objects without any counting. And this ability to recognize quantities without counting is called subitizing. It comes from a word meaning suddenly. And there's some other research supports this. Brian Butterworth from London worked with Australian Aborigine children who do not have counting words in their language, and he gave them counting tasks. They were able to do them. And the same thing was done with Gibson and Frank, MIT researchers in the Amazon. They also did it with adults in Boston. And there, to prevent them from counting internally, they asked them to listen to the BBC and to say out loud everything that they heard on the radio. And the last one, the baby chicks from Italy, a researcher at the University of Padova had the chicks could choose. These are just hatched chicks. They could choose whether to go to a large quantity of food or a smaller quantity of food. And most of them chose the larger quantity, more than half. Something else that's very interesting in this is for thousands of years, human beings have made quantities subitizable by grouping in 5s. First example of this, of course, is our hands. And this is really kind of interesting because we now know that the part of our brain that controls our fingers is right next to the part of our brain, the mathematical part of our brain. And I don't think that's a coincidence. Look how Romans wrote their early numerals. 4 is just simply adding 1 more line. But then when they got to 5, they used a different symbol. And then it was 5 and. See, 8 is 5 and 3. The Chinese abacus is hundreds of years old. Notice that you can tell how many beads are moved without having to count. The Russian abacus that has 10 beads, but they mark the middle 2, so you can tell where the 5s are. Japanese only use 4 at the most. It's very easy to tell how many beads. And as I said earlier, they were designed for calculation without any counting. Even the musical staff has 5, 2 groups of 5s. And if you're a piano player and you have ledger lines, you know how difficult that gets if you have too many. Even the keyboard is grouped in 5s. That's how you can keep track where you are. The 2, 3 is a group of 5s. Clocks. We can thank the Romans for clocks and for money. Tally marks are grouped in 5s. And tally marks are used throughout most of the world in various forms. But they're always grouped in 5s. Montessori also did some grouping in 5s. Mr. Yostin, who was the director of the Indian Montessori training course and my trainer, said that Montessori used the black and white bead stairs so the child does not need to count. I often thought about that phrase. Now, visualizing is related to this. Try to visualize 8 identical apples in your head without any grouping. You can't do 2 4s or anything else. I can't do it either. Now try to see 8 apples with 5 of them as red and 3 as green. Now, can you see it in your head? Most people can. With a little bit of practice, you can get pretty good at this. In other words, even our brains like groups of fives. Chunking. Grouping in fives provides chunking. According to psychologists, a chunked item can be stored or processed as one item. And 10, of course, can be reduced to 2 chunks. According to world memory champion Ben Pridmore, he says, think in pictures because our brain remembers images better than it does anything else. And visualizing is necessary for reading, sports, creativity, geography, engineering, construction, architecture, astronomy, archaeology, chemistry, physics, surgery. Would you want your brain surgery to be a person who couldn't visualize your brain? I don't think so. Here's a study that was done with college students. They wanted to see how long it took them to learn various things. They asked them to memorize 200 nonsense syllables. It took them an hour and a half. Then they asked them to memorize 200 words of text, less than a half hour. Finally, 200 words of poetry, 10 minutes. And the equivalent of poetry in mathematics is patterns. Look at the huge difference, 93 down to 10. And Ginsberg, a researcher, says the role of physical manipulatives is to help the child form visual images and thus eliminate the need for the physical manipulatives. The Japanese use one of this criteria for manipulatives. First, it must be representative of the structure of numbers, so they group everything in fives. Easily manipulated by children, of course, Montessori also does this, and imaginable mentally. That's one of their criteria. You do not see this in lists of criteria in the Western world. Here's another example where Montessori uses visualizing. You place the cylinder block on one table and the individual pieces on another. And then you put a marker in one of the holes and you go over there and try and find the one that will fit. And then, of course, remove the marker and put it in a different place. Instant recognition of a quantity is called subitizing. Subitizing from 1 to 5 is perceptual subitizing. And grouping in fives is called conceptual subitizing. 5-month-old infants can subitize up to 3. 3-year-olds can go up to 5. And 4-year-olds can go up to 10 with conceptual. And 5 and beyond can go even much higher. I want to show you as my little granddaughter did this. She was 3 years and 6 weeks old. She had not been taught this and she'd never done it before. She'd laid out 5 tiles and she knew it was 5. Then she moved one over and said, now there are 4. She moved another one over. Now there are 3. Another one. Now there are 2. Now there is 1. Now there is nothing. That's her word for 0. Benoit, a researcher, says subitizing allows the child to grasp the whole and the elements at the same time. Because remember, in counting, you concentrate on only one at a time. But with subitizing, you concentrate on the whole. And subitizing seems to be a necessary skill for understanding what the counting process means. That's assuming you're learning counting before you subitize. And it is true that children who are taught the counting do lose their ability to subitizing. Children who can subitize better perform in mathematics better long term. Counting on is a difficult skill for many children. It isn't even taught in the Japanese. And this is a really interesting. Math anxiety affects counting ability, but not subitizing ability. Colored bead bars are common in Montessori materials, but they are not subitizing. Using colors involves a different part of the brain. In Japanese schools, students consistently group in fives. They're discouraged from using counting for adding, and they're not even taught how to count on. So what is a good way to learn the quantities? I suggest we start with the left hand because we read from left to right. So this is 2, and teach the numbers using a 3-period lesson. This is 4, this is 5. And you must master 5 before going on because the other numbers depend upon 5. And most children know how to high 5. That's reinforcing the 5. So there's 7, and there's 10. And I wrote a little poem to help them memorize the counting. It's also set to music. Yellow is the sun, this is only one. And use your fingers while you say this. Why is the sky so two? Why is the sky so blue? Let me show you 2. Salty is the sea, 1 more and it's 3. Hear the thunder roar, here's the mighty 4. Ducks will swim and dive, my whole hand makes 5. Then this beyond 5. Yellow is the sun, 6 is 5 and 1. Why is the sky so blue? 7 is 5 and 2. Salty is the sea, 8 is 5 and 3. Hear the thunder roar, ducks will swim and dive. 9 is 5 and 4, excuse me. Ducks will swim and dive, 10 is 5 and 5. Tally sticks are a good way, but instead of having 5, wait a minute, this is a way to tell 5 from 4. 5 has a middle. 4 does not. And children as young as 3 years old can tell 5 from 4 using this. When we go past 5, when we go up to 5, rather than showing 5 like this, I use a horizontal. I use horizontal rather than diagonal because the stick doesn't fit. And horizontal lines are easier for children. So there's 7. You don't have to count. You can see right away 7. There's 10. And Montessori has a lot of charts, which is really a good idea. Einstein recommends this. But for a child who can't remember how to write the numerals, a chart like this would be a great help. Here's some activities we can do with using the groups of 5s. Finger cards. They're showing the fingers from 1 to 10. And if you make 2 sets of them, you can pair them in the traditional Montessori of doing this. And you can order them, put them in order. You can also match the numerals with the finger cards or match the cards with the numerals. And you can even play memory game. Now here are some modifications, simple modifications that can be done. This is the traditional number rods. But how about if we painted them like this? And we can see how much they are without having to count. Grouped in 5s. And then it's good to have one color dark and one color light. And this is a great help for children who have some color deficiency. And actually 1 out of every 12 children do have this. And often they don't know it. In fact, Michael Dorer, who was president of AMS a few years ago, did not realize he was color deficient until a teacher showed him as a parent-teacher conference, just wanted to show him that his son was color deficient. And they showed him the 8 in the mosaic, and Michael said, "What 8?" The spindle box also can be modified. If you use 35 blue spindles and 10 yellow, you can put them all together in a box. Or you can separate the 2. And then as a child puts them in, I like to have them use their left hand with the blue ones. So that's 1, 2, 3, 4. And then use the right hand for the yellows, the ones over 5. So there's 5, 6, 7, 8, 9. The stamp game. Usually the child puts them in a long path and adds them together. And then they have to count to get to the 10 in order to do the exchanging. Cheryl suggested that we use what she calls pyramids. See how much easier it is to do a trade? The bead frame. Here's a modified bead frame. The beads are grouped in 5s. To enter a quantity, first show the 3 on your hand and then enter it. There's 3, there's 5, there's 7. And the child is to enter them all as a group. They're not to count them out, but the whole 7. They look over at the beads and find the 7th one and move them all over. And there's 10. Children love to make stairs. That's why we have the pink tower. But something interesting, how about it when you read the quantity from top to bottom? What are you doing? You are saying the sequence. Simple adding. Let's add 4 plus 3. First enter 4. 3 more. Actual adding means sliding them together. And of course the answer is 7. Again, no counting. Part-hole circles are an interesting device, a tool that originated in Asia, and it greatly helps children solving problems, which of course is the main goal of mathematics when you think about it. Part-hole circles greatly help children. You put the whole in the large circle and the parts in the smaller circle. So if 3 and 2 are your parts, what's the whole? Obviously it's 5. What's the other part? If 10 is the whole and 7 is the part? It's 3. Now let's solve a problem. Alex received 3 goldfish as a gift. Now Alex has 5. How many goldfish did Alex have to start with? Now this is considered a very difficult problem, even for first graders, because it's what's called a missing addend. But let's take each number in turn and put them in the part-hole circles. Alex received 3 goldfish. Where should I write the 3? Is 3 a part or a whole? Well, it's a part. And where would you like me to write it? The left or the right? Most people suggest the left. I think it belongs in the right, but because it happens later, but most people don't. Doesn't matter. So let's look at the next number. Is 5 a whole or a part? 5 is the whole. Now, can we find the remaining part? Well, it's 2. Does that answer the question? Alex received 3 goldfish. Now Alex has 5. Alex had 2 to start with. That answers the question. Next, write the equation. There are many different equations you could write. I just wrote a few of them here. Research shows part-hole circles help young children solve word problems. Actually, the original research in the Western world was done with kindergartners. Writing equations does not, but we write equations. That's how we summarize what we're doing in mathematics. And never teach keywords to solve problems. Never teach that together means add. Actually, I'm one of those curriculum writers that likes to put the wrong keyword in. In real life, do you use a keyword to solve your problems? I hope not. Place value. In 1478, place value was considered one of the 5 operations of arithmetic. In fact, in that book written in 1478, The whole first chapter is just devoted on place value, all the way up to the billions. They considered it that important. Place value, not counting, is the key to understanding numbers past 10. Without place value, we are giving children numbers in bulk. I like to think of those bulk containers you see in the grocery store, rather than tidy chunks. We need to be sure children are learning place value, not color value. And it's best learned first by subitizing, initially using transparent number naming, composing quantities with bead material, then using the decimal cards, mastering the facts using base 10 strategies, and trading with 4-digit numbers, which of course Montessori does. This is just for humorous effects. The Common Core Standards for grade 1 says they should extend the counting sequence. In kindergarten, they had to go to 100. Count to 120, starting at any number less than 120, starting at any place. In this range, read and write numerals and represent a number of objects with the given numeral. Now, this is before they even cover place value, although you don't have to teach them in order. Understanding place value. Understand the following as special cases. I emphasize the word special. 10 can be thought of as a bundle of 10 ones, called a 10. Can be thought of? The numbers 11 to 19 are composed of a 10 and 1 and so on. Transparent number naming, in which 11 is 10-1, 12 is 10-2, 10-3, 10-4, and then the 2-10, 2-10-1, 2-10-2, and so on, all the way down to 9-10-9. This is the way the Asian children, the languages actually count. They change their languages. Sometimes it's helpful to say that 11 is 1-10-1, and other times just 10-1. I'm often asked about what do you do in the hundreds? Well, just add the 100 word. 100, 3, 10, 7. And it's perfectly fine to say 100 and 3, 10, 7. Here is some research that was done a couple decades ago, but the idea is still true. The Chinese at age 4 could count to 40. At age 5 up to 50, age 6 almost up to 100. The Koreans had 2 ways of counting. One was mixed up, like our English language, and the other was the transparent method. So at age 4, they didn't even count to 10. Age 5, about 30. And then they almost catch up to the Chinese after they start school. And it also brings them up in their non-transparent language, age 5 and age 6. But now the red are English speakers. Notice something special about that line? It's a straight line. They learn the same amount between 4 and 5 and between 5 and 6. In other words, going off to school did not do them much good. Some of the advantages are only 11 words are needed to count to 100 with transparent number naming. English requires 28. That's really tough if you're learning English as your second language. Asian children learn math with transparent number names. They understand place values several years before most American children. Even the Singaporeans, who are Chinese for the most part, but they attend school to immersion English, but they've already learned Chinese to count to Chinese at home. So they have this advantage, but they're not aware of it. And that's one reason the Singaporeans score so high, but they don't know the reason. Mathematics is a science of patterns, and number names should also be an example. A child is hearing impaired, often cannot detect the difference between 14 and 40 or 13 and 30. Compared to reading, I'd like to make this comparison. When we teach reading, reciting the alphabet does not help. Counting does not teach arithmetic. Just as we teach the sound of the letters, we must first teach the name of the quantity, which is the transparent naming. And Montessorians do this for a short while, but I really believe they must do it much longer. And incidentally, I like to say 310, not 310s. Don't put an S on it for several reasons. One is S's are often hard for children to pronounce. Another reason is they don't have singulars and plurals in the Asian languages. So I can translate it either way. And then it fits in with the other words. We don't say 327. We say 327. Here's what transparent number naming looks like on the modified bead frame. There's 40. And when we switch over to the traditional names about 3 months later, I'll say one day this is also called 40. This is also called 60. And the TY means 10. We have 3 ways of saying 10 in English. 10, teen, and TY, T. Then 310, we don't say 3D, we say 30. Another little confusion there. And ditto for 50. 210 is 20. And 2 used to be pronounced twoo. That's why we have twin, twine, 12. Now let's play a little word game. I'm going to say a word and you have to say that, reverse the syllables. So fireplace becomes place fire. Newspaper becomes paper news. Box mail becomes mailbox. This is what we have to do with the teens because they are pronounced backwards, thanks to the Romans. So 10-4, we're first going to change the 10 to teen, teen 4, and then we're going to reverse it 14. So that's 14. And let's do it with, that's also true with 16, 17, 18, and 19. Then we're left with just 2 numbers. Then you have to also change for 13 and 15. Then we're left with just 11 and 12. So I tell the children about 1,000 years ago, people were trying to think of a good name for this number. And they said, let's name a 1 left because it's 1 left over 10. But then they reversed it. And then they said a left 1, which became 11. And that's a derivation of the word. And 12, remember we used to say two. So two left became 12. And it's the only one of the teens that isn't said in reverse order. 310. And using the place value cards or the decimal cards, 310. I like to point to each one as I say it. 310. 310, 7. The 7 goes on top. And I question whether we really need to have that green. Montessori said needless help is an actual hindrance to the development of natural forces. There's 37 of the same color. But notice the congruence, how what we say, how we represent the number, and how we write it all match beautifully. Another example is 110, 8. Put the 8 on top. There's our 18. Now, can you quickly say how much this is without any counting? You can tell it's 43. Or here's a harder one. That's the reason we changed the color of the beads after 5, because you can see right away it's 7, 710, 70, 76. Here's 1010. Learning the facts is limited success when we're using counting or skip counting or dots or fingers or songs or number lines or all kinds of things. And when it's based on rote memory, flashcards, or time tests. Instead, we need to use strategies. A strategy is a way to learn a new fact or to recall a forgotten fact. Effective strategies are dynamic and visualizable. Here are 3 major addition strategies. Partitioning 10. 10 is 4 and 6. This is one of the most important set of facts to learn to start with, ways to make 10. So 10 is 4 and 6, and it's also 8 and 2. The second strategy is complete the 10. Let's try 9 plus 5. If I have 9 and 5, if I take 1 from the 5 and give it to the 9, then I have 10 and 4. And this, after a while, can be done without even moving the beads. There was a boy with learning disabilities in first grade when I did my research who could add all his numbers up to 9 by using this method. The teachers were amazed. 8 plus 6 using 2 5s. You can see the two sets of blue beads make the 5s. So all you have to be concerned with is how many over 5 it is. 3 and 1, so it's 14. This strategy is commonly used in Asia. And subtraction strategies also has 3 major strategies. One is going up. This is what we do when we make change. 15 minus 9. We'll start with 9. And what do we need to get up to 15? We need to keep track. Well, we need 1 to get to 10. That's why we need a door of facts to make 10. And then 5 more. So 1 and 5 is 6. There's our answer. That's the difference. Subtracting part from 10. This is not very exciting. There's our 15, and I subtract as much as I can from the 5. It's almost like counting backward, which I don't recommend. And then subtract what I need to get my 9 from there. Again, my answer is 6. Now subtracting all from 10. How about just taking the whole 9 from the 10? And then I can see I've got 1 and 5. And if you look at the numbers, take 9 from the 10, you've got 1, and add it to the 5. This is what was done in the Middle Ages. They never memorized any facts past 10 minus. They never memorized the 11s or 12s or so on, because they always used this method. And notice how all the addition and subtraction strategies are based around 10. They're all based on place value. Okay, side 2 of the modified bead frame. There's the thousands, 2 wires, 2 wires for the hundreds, 2 wires for the tens, 2 wires for the hundreds, for the ones. And then there are 2 wires that are not used. And that seems to bother the adults more than it does the children. So 8 plus 6, there's 8, there's 6. And notice we slide them up together. Actually use the thumb to move them up. Actual adding, there they're added. And we can see our answer immediately as 10 and 4 or 14. But too many ones, we want to do a trade. I prefer the word trade to exchange because a child knows when a trade is fair. But exchange, they don't have any meaning for that. And remember, the words that we use are translated from Italian. So Montessori didn't actually use that word. But I asked one boy who had been using exchanging. I said, what does exchanging mean? And he immediately gave me a math example. Nothing else made any sense to him. And it does not imply equality. Also, the word trade is phonetic. So we get ready, get set, and do our trade. And again, we can see our answer is 14. Of course, it has to be the same before or after a trade. You'd be amazed the number of children who do not realize that. Now let's try the same problem on the bead frame. Let's add our 8. Now we can add from our 6, we add our 1 and one more. Now we have to do a trade and then continue counting. 3, 4, 5, 6. And then see our answer as 14, 1 10 and 4 ones. Now there's a few difficulties with this. First of all, they're not visualizable. Beads need to be grouped in fives. When beads are moved right, they're inconsistent with the order of the equation. Montessori herself said that beads should be moved to the left, but there are trainers who move the beads the other direction. I had a rather interesting conversation with a trainer in Canada. The background is visible through the frame when the child is working with this. For a child with ADHD, it's very distracting. So it should be flat. Hierarchy numbers are represented sideways. I had trouble with this myself when I was in training. The column should be vertical. We don't write numbers sideways. And exchanging is done before the second number is completely added. This is where a lot of children have trouble. I can't remember where they were. Well, we don't add numbers. We don't exchange or trade in the middle of the second addend. We put them together and then do the trading, both on paper and mentally. And the answer is read going up. We don't read going up, we read going down. Look at your freeway signs when it's 3 digits and they just have a narrow sign. You read going down, not up. So would you like to see how to add a 4-digit number on side 2? Let's add 3,600, 510, 8. And we add the numbers in the normal order, which is what you do on Asian abacus too, incidentally. Now let's add the second number, and you'll be happy to know we'll start from the right, although you could start from the left, but we'll start from the right. Let's add 8 ones. You can see that do we need to trade? And it's very important that we write down at each step what happens. So let's do our trade. Get ready, get set, trade. So what do we write down? 6 ones. Did anything else happen? Well, we have another 10. Is it okay if we write that 10 with the other 10s? Nobody's ever disagreed with that. All right, let's add our 10s. Let's add our 3 10s. What do we have now? Do we need to trade? No, we don't. So what do we write down? 9 10s. And it's important to say 10s too. All right, what do we do next? Let's add the 700s. Do we need to trade? Yes. Notice how you can instantly see it. Let's do a trade. Get ready, get set, trade. What do we have to write down? 300. And what else? Another 1,000. And lastly, add our 2,000. And what do we write down now? 6,000. So our answer is 6,396. Kindergartners, I gave them a week. After a week, they were all able to do this on paper and pencil, without using the abacus. I've had parents of other children doing this, and they said some children catch on in one day. Memorizing math. Flashcards are often used to teach rote. The only person that likes them is the person who doesn't need them, and they don't work for children with learning disabilities. They give the false impression that math is something you're not supposed to think, you're just supposed to know. Nothing could be further from the truth. And they produce stress. We now know that children under stress stop learning. And they're not concrete. You're asking them to memorize symbols. Let's take a look at some multiplication strategies. There's 8 times 4, or 6 times 4. Do you see some 10s there? So you can see without any counting, 6 times 4 is 24. Let's try 9 times 3. Well, I know the whole row is 30. I simply subtract a 3. I've got my answers, 27. Let's try 4 times 8. You see any 10s here? Yes, there are some. About right there. That's 20. And then down below we have 12. So my answer is 32. Every fact can be done like this. And it's kind of a nice little puzzle. 7 times 7, my favorite. That's the binomial. You know the blue beads are 25. You've done this enough. And you see a couple other 10s. So it's 25 plus 10 plus 10 plus 4. Remember, a child is considered to know a fact if they can give it within 2 to 3 seconds. And you can easily go through this in your head. You can see this arrangement in your head and think 25 and 35, 45, 49 in less than 2 to 3 seconds. The commutative property, 5 times 6. I still think this is amazing that this is true. 5 times 6, you can see 5, 6 times, is the same thing as 6, 5 times. Now contrast this to the multiplication board. There's 6 times 4. But if you use 2 colors, 7 times 7, kind of overwhelming. But again, if you use 2 colors, there it is. You really don't even need, you don't even need the numbers on top. Some questions for the Montessori community. Montessori used words and items that were familiar to the Italian population. Nostalgic language may be an obstacle for our children and families. It could be confusing or even archaic. Summary. Infants naturally subitize and visualize. We must help the child nurture these gifts because they will lose them. We do not nurture them. Visualizing requires grouping in 5s. Effective strategies for mastering the facts are visualizable. Visualizing is critical for obtaining abstraction. And visualizing greatly helps our disadvantaged children because it reduces the heavy memory load. Dr. Montessori made invaluable contributions to the welfare of children. Every great movement struggles with staying true to its core principles while staying relevant. We now know that counting is not the best way to teach arithmetic. And the pedagogy of science and mathematics must be updated periodically.